Welcome to another lecture for CyberAI. In this video, we're going to discuss anomalies and anomaly detection. At its heart, anomaly detection is really just the process of finding things that don't look like the other things. Finding one of these things is not like the other. That classic saying that you might have learned as a preschooler. That's what we're doing with anomaly detection. And especially in cybersecurity, the same idea holds. Networks, systems, and people have normal patterns. When something falls outside of that normal pattern, we call it an anomaly. That's the core, really, of what we're going to explore. An anomaly is simply something that's unusual or unexpected compared to the majority of what you would normally see. Imagine you're looking at a set of logins. You're looking at an authentication log, and it contains successful logins. If you have 1,000 logins and 999 of those happen during the day, one happens at 3 in the morning, that single entry is an anomaly. But here's the key point. Being an anomaly doesn't always mean bad. Sometimes anomalies are just quirks or rare but harmless events. For example, if you travel overseas, your login might look weird because it's from another country, but it's still you. On the other hand, anomalies are often the first signs of trouble because attackers rarely look exactly like everyone else. Their traffic would rarely look exactly like everyone else. So in cybersecurity, anomalies are important because they hold a goldmine of both good and bad surprises. We need to treat them carefully, neither ignoring them nor overreacting. Why should we care about detecting anomalies in the first place? Well, in cybersecurity, attackers want to blend in. Think of them like shoplifters in a store. They don't want to wave a flag saying, "Hey, I'm stealing." I don't know if there is such a flag, but they don't want to wave that flag. Instead, they try to look like every other shopper. But even careful shoplifters leave traces. Maybe they move in an unusual pattern. Maybe they avoid eye contact with employees or avoid employees altogether. Or maybe they're fidgety at the checkout. On a network, the same thing happens. Attackers send traffic that mostly looks normal, but maybe the timing is unusual, or the data volume is unusual, or maybe the destination is unusual. Traditional rule-based systems can miss those types of tricks. Rules and signatures only catch things that we already know about. Anomaly detection is powerful because it doesn't rely on yesterday's rules. It surfaces unusual patterns right now, even if they've never been seen before. That means we can spot attacks faster before the damage spreads, and in a world where threats change daily, that's a big advantage. In cybersecurity, anomalies appear in many places, so let's list a few. Maybe in logins, where a user normally logs in from Wisconsin, but suddenly logs in from a different country. Well, that would be unusual. On a network, you might see a new device that no one has ever connected before. That stands out. The ARP entry, the MAC address, might be different. On an endpoint like a laptop, where you might see a word processor suddenly try to launch a command shell, which is not what you would think a word processor would normally do. Maybe in email, you might see a reply that looks like it's part of a normal thread, but the domain name is slightly off. In DNS queries, you might see thousands of odd subdomains, random strings of characters, all requested in a burst. Those types of things are anomalies. Some of those will be false alarms. Some of those will be normal traffic or turn out to be normal traffic, but some are the very first evidence of an attack unfolding. That's why anomaly detection is so important. It helps us shine a spotlight on the weird corners of our data. 3 big questions then. Let's introduce those big questions that frame our anomaly detection. And you really don't even need math to understand them, just plain intuition. First, distance. How far is this event from what we normally see? If most logins cluster around certain times and places and one login is way off, well, then that's a distance anomaly. Density is another question to ask. How crowded is the neighborhood around this event? If an event lives in a crowded cluster of similar events, it's probably normal. But if it's lonely, if it's far from any neighbors, it's suspicious. And third, reconstruction. If I've learned what normal looks like, can I rebuild this event from memory? Imagine you memorize the structure of normal logins. If a new login fits this pattern, you can reconstruct it. If it doesn't, you fail, and that failure is an anomaly signal. These 3 questions, distance, density, and reconstruction, guide almost every algorithm that we'll be covering during this or future lectures. Keep them in mind, and the methods then will make sense. Let's connect anomaly detection then to something that you already know from previous videos. Earlier, we defined a data set as having rows and columns, like a spreadsheet. Each row contains an example, so each row would be an entry in a log file. Each column is a feature. We labeled those features through an exercise. Each column is a feature. That's what we would call it in this context. A measurable property, maybe like byte sent, port number, source IP, time of login, those types of things are all features of our data. Anomaly detection works on those features. It doesn't work on raw text or logs. That's why feature engineering is so important. If you choose meaningful features, anomaly detection works beautifully. If your features are poor, even the best algorithm won't help with your anomaly detection. You can think of it like cooking. If you start with fresh, high-quality ingredients, even a simple recipe can taste amazing. But if you start with things that are spoiled already, well, no amount of fancy cooking will save it. Features are your ingredients. Anomaly detection is the recipe, and you need both to get a good result. Here's another look back then from an earlier week. Remember unsupervised learning? Well, that's when we don't have labels telling us what's good or bad. We just look for structure in the data. Anomaly detection is essentially a form of unsupervised learning. We're saying, here's a big pile of data unlabeled, so we don't know if it's good or bad. We want to know which parts don't fit the structure. That's what makes it useful in cybersecurity. We rarely have labels. No one hands us perfect data sets saying this row is an attack, this row is safe. We usually have messy logs with no labels whatsoever, sometimes completely different formats, and we have to programmatically get all of those things into the same format so we can identify the same or common features. And we've discussed similar tasks and even demonstrated similar tasks already. So anomaly detection is where supervised learning can't go. It helps us to discover the weird things without needing someone to label every single event in advance. That's where unsupervised learning helps. That's why it's one of the most practical tools for defenders. So now that we have that little bit of introduction or intuition behind what we're doing, we can start building toward the methods that we will use. Think of it like this. Distance-based methods are just ways to measure closeness. They might ask, how far is this login from the usual pattern for this user? Density-based methods are ways to check how crowded the neighborhood is. They might ask, is this process behavior isolated compared to others, or does it live in a dense cluster of similar activity? Reconstruction-based methods are ways to test memory. They might ask, if I train a model to memorize normal patterns, does this new event fit, or does it stick out? Would it be an anomaly? These questions sound simple, but they map directly to well-known algorithms that we use when we're building models. K-nearest neighbors, or KNN, is something that you'll hear. Local outlier factor, principal component analysis, we talked about already, or PCA. Also autoencoders. All of those well-known algorithms relate directly to anomaly detection. Once you keep the big picture in mind, those three questions, distance, density, and reconstruction, well, then the specific algorithms are much, much easier to understand. So let's recap here our introduction. Anomaly detection is about finding weird stuff in data. We've defined what an anomaly is. We've explained why it matters with a couple of analogies, and also show where those anomalies appear in cybersecurity. We've introduced three big questions: distance, density, and reconstruction. Those frame everything else, and we've connected back to some of the earlier material that we had on features and unsupervised learning. So you can see where this fits in the bigger story of machine learning. Next, we're going to dive a little bit deeper into anomaly detection, explore each family of methods in turn, and we'll talk about some distance-based methods like nearest neighbors, and maybe explore other methods. We might talk local outlier factor and PCA, autoencoders, those types of algorithms we'll be talking about as it relates to anomaly detection. So thanks for watching, and we'll look for you in the next video.